So I think the specific question I had then and still have is that the most impressive algorithm we have, which is seemingly can do exponential number of different things, is linear algebra, which we learn in high school. And so the question is, why can't linear algebra solve NP-complete problems? And so this would seem even a simpler problem than the general problem. What is the connection between P and NP? So basically, I think this is what I was trying to find out. So early on, I found this permanent function, which was a pretty obscure function at the time, which not much was written about. So combinatorialists knew about it.
Do you remember where you first became exposed to it?
Actually, I don't. I think I presume I kind of invented it and then realized it was well known. That I came across it somehow. But I remember, so maybe it was in 1976, I met Dominic Welch at a workshop, and he was a combinatorialist, and so we had a discussion. And so at that point, I didn't know which way I was going, what easy, what hard. I mentioned to him this permanent and determinant, and his comment was, so if I can reduce the permanent to determinant efficiently, so I can compute the permanent fast, that would be a publishable result. Okay, so it turned out that I had to go I went the other way. But the specific problem I was working on is that there's no reason even now for believing that you cannot do NP-complete problems with linear algebra.
Not just in linear time, but in fact in linear time with linear algebra.
Well, it doesn't have to be linear time, but linear algebra in a certain amount of time. So in some sense, the Sharpe completeness came out of a failure to get positive results.
I see.
Yeah. So first I got the result about the permanent using some very kind of technical reduction. And then I started thinking about other problems, which are counting problems, and where did they lie? So lots of problems which are where you compute probabilities, reliability of a network breaking down,
Right.
and counting, all kinds of stuff.
Right.
So this was kind of So the surprising part was that at the time people thought that NP-completeness is one exponential difficulty. The idea of finding NP-complete problems where actually finding solutions is easy, but just counting them is hard, was something which wasn't seriously addressed. And so I remember once to a well-known person describing this in a train to a conference, and they said, "Oh, something must be wrong here."